Hello everyone, welcome to B.Tech. So in this video, we are going to see how the op-amp acts as an adder. So we have up to now we have seen how op-amp acts like a subtractor. It is also known as a difference amplifier. Now we have seen op-amp acts as a voltage follower or buffer. Now in this video, we are going to see how the op-amp acts as an adder. So what is adder? So the circuit which adds the given input signals. Either we give 2 inputs or 3 inputs or 4 inputs. So if the circuit the output voltage is proportional to the addition of the given 2 inputs, we can say that that circuit acts as an adder. So this adder is of 2 parts. One is inverting adder and the one is a non-inverting adder. Similar way, for an inverting adder we provide the inputs for inverting input terminal, and for a non-inverting adder we provide the input terminals for non-inverting terminal. So here at first we are going to see the inverting adder. So for an inverting adder, so I am considering the input voltage are provided for inverting input terminal and the non-inverting terminal is made to ground. So here I am considering 2 inputs here, V1 and V2, which are provided only for inverting input terminal. So the remaining circuit is same. So considering the op-amp as an ideal. So we have to consider the op-amp as an ideal. So when we consider the op-amp as an ideal, the voltage at node A, VA, is equal to voltage at node B. So here we are seeing that the voltage at node A is made to 0. That means as VA is made to ground, so VA is equal to 0. As VA equal to VB, we can write VB is equal to 0. According to ideal op-amp characteristics, we can write VB equal to 0. And a similar way, I is equal to IF. So here I consider this current as an I. So I equal to IF. So now first write down the expression of I1. So I1 is a current. So I1 is a current starting from V1 and ending at VB. So the expression of I1 can be written as I1 equal to V1 minus VB by R1. But what is the value of VB? The value of VB is 0. So here we can write I1 equal to V1 by R1. So that is the value of expression of I1. In the same way, write down the expression of I2. So I2 is a current starting from V2 and ending at VB. So I2 is equal to V2 minus VB by R2. But what is the value of VB? VB value is 0. As VB value is 0, we can write I2 equal to V2 by R1. So at node B, so the I current, what is the expression of I? I is the combination of I1 and I2. So I is equal to I1 plus I2. So we have derived the expression of I1, we have written the expression of I2. By adding these two things, we get I. I is equal to V1 by R1 plus V2 by R2. So in the similar way, the current IF. So IF is a current, feedback current, starting from VB and ending at V0. So we can write IF equal to, so IF equal to VB minus V0 by RF. So as VB is equal to 0, we can write IF equal to minus V0 by RF. And similarly, already I said I1 equal to IF. So already we have derived the expression of I and already we have derived the expression of IF. We can equate these two expressions. So I1 and this one is IF. Equating I equal to IF, we get the value of output voltage V0. So V0 equal to minus of RF by R1 into V1 plus RF by R2 into V2. So if we consider all the ratios are equal in the cycle, that means R1 equal to R2 and R2 equal to RF. If we consider all the ratios are equal, we get V0 equal to minus of V1 plus V2. So by seeing this output voltage expression, we can say that the output voltage V0 is equal to the addition of the given 2 input voltage with a negative sign. That means the negative sign indicates the phase shift between input and output. As there is a phase shift between input and output, we can say that this adder, as it is adding the given 2 input signals, it is known as adder. But as there is a phase shift between input and output, we say that it is an inverting adder. So that is an inverting adder. Summa, it is also summa. Next we will go for non-inverting adder. The same way, non-inverting adder means we provide inputs for non-inverting input terminals and the inverting terminal is made to ground. So here the inverting terminal is made to ground and the input voltage V1 and V2 are provided for non-inverting input terminal. Similar with this. So in the same way here also, consider the op-amp as ideal symbol. As the op-amp is ideal, we can write first case I equal to IF, as well as the voltage at node A is equal to voltage at node B. Now we have to calculate the voltage at node A. So how the voltage at node A is calculated? So first down, write down the expression of I1, same. I1 is a current starting from V1 and ending at VA. So I1 equal to V1 minus VA by R1. In the similar way, I2 is a current starting from V2 and ending at VA. So it is equal to V2 minus VA by R2. So according to ideal op-amp characteristics, the currents entering into the input terminals of op-amp is 0. That means here I1 and I2 coming at A, that means they are both are combining with each other, I1 plus I2, and entering into the op-amp input terminals. As these two currents are entering into the op-amp input terminals, we can take it as I1 plus I2 equal to 0. So already we have derived the expression of I1, we have derived the expression of I2. By substituting I1 and I2, we get here. So by solving this one, we get VA equal to 1 by R1 plus R2 into V1 R2 plus V2 into R2. Now the current I is expressed as, so I, So here this is the current is I or I, this one is the current. I is the current flowing from ground towards B. So I equal to, so ground voltage means 0, 0 minus VB by R. So in the place of I we can write 0 minus VB by R, the expression of current I. So here the current I is minus VB by R. In the similar way IF is the current flowing from B and entering at V0. So VB minus V0 by RF, as I equal to IF, because according to ideal op amp characteristics we consider as I equal to IF, as I equal to IF. So I and IF, substituting these two things and doing some mathematical operations, we get VB equal to V0 into R by RF plus R. So we know that as VA equal to VB, so in the top we have derived the expression of VA, and here we have derived the expression of VB. According to ideal op amp characteristics, we consider the voltage at node A is equal to voltage at node B. So VA equal to VB. Then equating 1 and 2, we get the output voltage expression V0. Similarly, so consider all the ratios are equal, R1 equal to R2 and R2 equal to RF. So by considering all the ratios are equal, we get V0 equal to V1 plus V2. So now by seeing this expression, we can say that the output voltage is equal to the addition of the given two input voltage without any phase shift. As there is no phase shift, we can say that as this circuit adds the given two input signals, we can say that this is an adder, and as there is no phase shift, we can say that it is a non-inverting adder. So the difference between the inverting and non-inverting adder means both adds the given two signals, but in an inverting adder there exists a phase shift between input and output, but whereas in non-inverting adder there exists no phase shift between input and output. So that is the non-inverting adder. Now we are going to see a simple problem using this adder and subtractor configurations. So here a problem is asked, design a circuit which generates an output V0 equal to 2V1 minus 3V2 plus 4V3 minus 5V4. So this is the expression given. So now we have to design a circuit which generates output voltage V0. So this is the output voltage V0. So these are given in the problem. So now we have to design. So now divide the coefficients, positive coefficients and negative coefficients one side. So by dividing the positive coefficients, so V0 equal to 2V1 plus 4V3 in one case, and minus of 3V2 plus 5V4. So here we got minus 3V2 and minus 5V4, and by taking minus as common, so we have derived the positive coefficients and negative coefficients here. So these two things. So we see that, so here we have to use an adder which adds the given two signals, and here also we have to use an adder which adds the distributed signals. So let us design an adder whose output voltage is equal. So now I have divided this output voltage into two parts. So V0 is divided into V01 minus V02. So V01 is considered as 2V1 plus 4V3 and V02 is considered as 3V2 plus 5V4. So this is, so the output voltage is the inverting adder. Now we have to derive. So first by solving this expression, for solving this one, so do we consider V01 as negative 1. So as seen, the output voltage of inverting adder. So what is the output voltage of inverting adder? V01 equal to minus RF by R1 into V1 plus RF1 by R3 into V3. So this is the voltage already, the expression of voltage already we have derived if the ratios are unequal. If the ratios are equal, we can write V0 equal to minus of V1 plus V3. But we should consider, because as the gains are separate here, different way. So the two ratios which we are going to use are different with each other. So comparing 1 and 2. So here comparing 1 and 2, we get RF by R1 equal to 2 and RF1 by R3 equal to 4. Here we get R1 equal to RF1 by 2 and R3 equal to RF1 by 4. Consider the feedback resistance RF1 equal to 100 kilo ohms. As RF1 equal 100 kilo ohms, we can write R1 equal to 100k by 2. So we get R1 equal 50 kilo ohms and we get R3 equal 25 kilo ohms. Now first draw the circuit of inverting adder. So this is an inverting adder. Now let us design the adder whose output. So we are using only inverting adders here. So here, and again V02 is considered here. So V02 equal to minus of 3V2 plus 5V4. In a similar way, this is the output voltage expression of an inverting adder. By comparing 3 and 4. So by comparing 3 and 4, we get RF2 by R2 equal 3 and RF2 by R4 equal 5. Next, let RF2 equal 120 kilo ohms. So if we consider RF2 equal 120 kilo ohms, we get R2 and we get R4. So this expression can be of your choice. It's not that I have taken here RF1 equal 100 kilo ohms and RF2 equal to 120 kilo ohms. So we have to, you should also choose these two things. It is of your choice. You can take any of the value which is greater than 100 kilo ohms, because RF feedback resistance of op amp is very high. So we have to choose that one more than 100 kilo ohms. So here we got the expression of R2 and the expression of R4. And this is the inverting adder. So this is inverting adder which generates this output voltage. Now to get the required output voltage, we have to use a subtractor. We have to use a subtractor because V01. So here at the starting stage we have seen that V01 is a positive and V02 is a negative voltage. But in the similar we have derived V01 as a negative inverting adder, and for V02 also we have used a non-inverting adder. So for both the cases we use an inverting adder, and here V01, the phase shift of V01 should be changed. So to change the phase shift of V01, so to use a subtractor. So now I am using a V02 subtractor. V01 is provided for inverting terminal because the phase shift of V01 should be changed. So as a phase shift of V01 should be changed, it should generate to a inverting input terminal, and the phase shift of V0 should not be changed. So V02 is provided for non-inverting input terminal. So by substituting these two things for a subtractor, we get V0 equal to V02 minus V01, and by combining all the circuits, so there is a circuit which generates the given output voltage V0 equal to 2V1 minus 3V2 plus 4V3 minus 5V4. So this is the circuit. Okay, thank you.